Well, today I'm going to talk about our recent results on using machine learning to identify different kind of lights. Sounds very simple, but I will tell you why it's not. So yeah, we recently started our group. We work on free space optics. We work on quantum state engineering. That's why we're doing this kind of work, and we do quantum lattices like optical chip stuff, and we do quantum networks. This kind of quantum plasmonic devices, and all of these. The work I'm presenting is a building stone for these future works we're working on. So that's why it's very important to us. So when we talk about quantum,
can you go back one slide?
Sorry, what?
Can you go back one slide?
Yeah.
The second person there, by the way, was a Tulane undergraduate.
Yeah.
Who just started graduate school at LSU.
Yeah, it's pretty good. But he's struggling with courses and experiments. It's very hard to balance between them. So yeah, when you talk about quantum fluctuations of
light. So
light.
you're saying Tulane did not prepare him?
I didn't say that. Well, I guess for all the grad students, the first few years are very hard because you have to do a lot of coursework. Right? So yeah, back to the slides, right? So we have different kinds of light, as we all know. The first one, the most common one, like sunlight, thermal light. And then we obviously have laser, coherent light. And then we have single photons, or we have like this molecular fluorescence light, these kind of light. So it's kind of, you might think it's really easy to identify these kind of light, but that's true in some cases. For example, if you have extremely high average photon numbers, obviously you can take few measurements and you can immediately tell them apart because for the coherent states, the mean of the photon number will always be, the most probable photon number you detect is at the mean of the coherent state, right? And then for thermal, if you plot the distribution, the highest will be always at 0. It's a vacuum. And for the single photon or like fluorescence, it's just single photons. It's easy, but to experimentally reconstruct the photon statistics of a particular light field is actually a very resource-intensive task. For example, in this 2005 PRL by Paris group, they were trying to do this kind of reconstruction of photon statistics. But in their work, they have to do these kind of method with around 10 billions of measurement to reconstruct even one slice of the photon statistics of your state. So that means you have to take probably a few hours of your data, and then you have to spend a few hours of computational time, and then you can determine, oh, I have a thermal state, or oh, I have a coherent state with these kind of photon number distribution. And another thing is to tell different kinds of light, you can resort to this Mandel Q parameter, where for the thermal state, obviously you have the Q equals to n average, and then for coherent you get 0, and for Q less than 0 you get some kind of quantum light. So and these the Q parameter is when Omar was at NIST, they actually did this Mandel parameter to certify the source they have is quantum. But in that experiment, they also took millions of measurements, which I will, briefly introduce. So these works are kind of inspired by the recent work Omar did while he was in NIST. So we recently published in NPJ. So we did multi-photon quantum state engineering. But in this case, if you have kind of two-mode squeezed vacuum and then you subtract photons, obviously you change the photon number distribution of your state, right? And then to reconstruct these kind of states or tell what kind of states we have, in this case, they did 20, 30 millions of these measurements for each cases, and then they have to reconstruct it by PNR, photon number result detector, which is there's probably 3 or 4 in the world. So you kind of need a lot of resources, hardware-wise and computational-wise, and you can reconstruct these. So people have been working on this kind of.
So
Yeah.
quick question. Can you go back to the previous slide?
Mhm.
These are pictures of the density matrices of two-mode squeeze vacuums.
These are not density matrices. These are the photon number probability distributions. Joint. The top
on
one.
a two-mode state.
Yeah, it's a 2-mode state.
Okay.
Yeah, the top one is experiment and and the theory.
Okay. Thank you.
So yeah, people have been doing this kind of things. Well, the first one I mentioned earlier, they use, for example, like here mean is around 5-ish, mean for the number 5, and then they use 10 to the 6, if I remember correctly, to reconstruct, the distribution for coherent state. And then recently, there's another PRL paper. They are talking about accurate detection of arbitrary photon statistics. They also use around 10 to the 6 measurements to they have an input state, arbitrary of course, and then they have a multi-pore network. You have a beam splitter network, and then you record all the traces in your oscilloscope, and you try to analyze. Based on the traces, you do a histogram, and then you convert it to click statistics, and then you go back to the photon number distribution, and that takes a lot of time and resources. And for some tasks, obviously you need this kind of statistics, right? But for other tasks, I just want to tell, okay, what is this state? Is this thermal state or it's a coherent state? So in that sense, these kind of works inspired by this machine learning algorithm and this kind of optimization algorithm. It actually helps a lot in this kind of resource-intensive tasks. For example, like earlier this morning, Sanjay was talking about like how he can use machine learning to help with do the quantum tomography. And then in this work, I think Omar was also a co-author. They were doing compressive sensing on characterizing the telecom photon pairs they have. And then there's a group by a Chinese group. They use this kind of machine learning to tell if you can violate the belt inequality or not. Also experimentally. So these kind of work suggests that machine learning could help us to reduce the number of measurements you took for these simple tasks. And why is that important? Okay, for example, in the NatureCon in 2014, Morris and they did a imaging with small number of photons. And here, by saying small number of photons, they mean average photon number less than 1. So you do these kind of imaging in extremely low photon number regime. And then you can also do compressive objective tracking using entangled photon pairs. So here, obviously when I say entangled photon pairs, it's on average of close to 1. So these kind of work also requires if you want to do imaging, you want to quickly reconstruct the image, even if the average photon number is very low. But if you go back to reconstruct the full photon statistics, that will take a long time, and these will contrary to each other. So that's where we want to see if we can improve it. So for example, one particular example of this is like when you have this kind of LIDAR kind of situation. And then obviously for LIDAR you use your laser, right? But then that's coherent state. But you will have thermal emitting from the sun or reflected from the the environments, and then you want to tell them apart. Maybe at some point, if you work in a low photon regime, you want to tell them apart, and that's really used. In that situation, this kind of technique might be very, very useful. Yeah, enough of the intro. So our setup is actually pretty simple. So basically, you just have a laser, and you have a beam splitter, you divide it into 2, and then using our rotating ground glasses, and you can basically simulate a pseudo-thermal light. And in the other arm, you just don't do anything because you need a thermal and a coherent. And then here's our setup, pretty simple. And to achieve this kind of machine learning to discriminate or identify if the state is coherent or thermal, we use what we call ADLING, so adaptive linear element. It's a very simple model of this machine learning, or you can call it, well, I think it's machine learning because this part's adaptive kind of to me. So ADLINE is a single neural network based on a linear processing element. So it's very good for these kind of binary, for binary classification, which in our case, we just want to tell if the state is coherent or thermal. Sorry. And then, when you have two states at relatively low mean photon numbers, if you plot the photon number distribution probabilities, you realize, the lower you get, these thermal state and coherent states, they look exactly, they look closer and closer. And in the region of where it's extremely small, for example, if you look at D, if you take just few measurements, you can't tell it apart because the majority of your result will be 0 and 1. You cannot tell them apart. But obviously, when you see when it's relatively higher, if it goes to 0.77, you see this 0 result and 1 result, it started kind of deviates from each other. So and then obviously when the n bar is extremely high, as I talked in the beginning, for thermal it's going to be 0 most of the time, and then for coherent you have a Poissonian distribution. It's based where the center is at n bar. So here we just focus here into the low photon regime. And in this plot, we have experimental reconstructed results together with the theory prediction based on the mean photon number. The theory is the dashed lines, and then the bar plot is the experimental reconstruction. You will see these. Here we used a trick I didn't mention before, but it's based on when your laser have a coherence time, and then your detector is, your detection dead time is much faster than the coherence time of your laser, then you can effectively use that single photon detector as a multi-photon detector. So and it works pretty well in mean photon number less than 4 or 5. But once your average mean photon number goes higher, the fidelity goes lower and lower. But for our project, this is good enough. And then to illustrate the idea I just said, right? So if you take, for example, if you take 100K measurements, obviously you reconstruct either the coherent state distribution or the thermal state distribution, because you have enough measurement, you can reconstruct a very good statistics. But then, what if you only have 10 measurements? It could look like this, which is, in this case it's similar, but in the thermal case, you see, it doesn't tell you anything. You can misinterpret this as some unknown states. So this tells us if we can somehow, without avoiding doing 100K measurement, we just do let's say 100 measurement, but with relatively high confidence of telling us what is coherent, what is thermal. That would be that would reduce a lot of our the time we spend on the experiment taking the data analysis. So to do that, we did a few approaches. The first one, we really want to set a baseline performance of our machine learning. You can't arbitrarily just say, okay, here's our method and here it works, right? You need to have something to compare against. So the first thing we did is a naive base classifier, basically just a maximum likelihood. So based on the photon number distribution you have, you just estimate, it could be thermal or it could be coherent. You pick the higher one, and then you repeat for all these data set you have, and then you plot this, this accuracy plot. You see, kind of makes, well, I think it makes sense to me at least. So when you increase the number of data points, the confidence of you discriminating if it's thermal or coherent goes up, and then when the average photon number increases, and naturally the accuracy grows because it's easier to tell them apart when the mean photon number is larger. But then we want to see if our line helps or not. And then we basically we did the same thing. We divide the data in the same way, and we train the line. And you will see, in the low photon regime, it doesn't really help. In the low number of points, it doesn't really outperform the naive base classifier. But when you have relatively high, let's say when you have near 100 measurements, then you can see this line performs significantly better than the naive base. And then you might ask why the naive base or why line works. So if you remember earlier, I was saying line is a linear classifier. So basically that means you have 7 this kind of feature input, and you train the weight between them. But then you can really plot these kind of input features on a hyper plane to help you to see if actually these kind of these thermal and coherent input actually is living to 2 different spaces. And you see once you plot it, I mean this is only 3D, so it's P0, P1, P2, and then but once you plot it, you will see it's kind of it's linear separable. So for 0.4, I mean it's hard. That's why the accuracy is low. But when you have relatively high mean photon number, you can see it's linear separable. And then you can further confirm it by instead of going to different mean photon number, you can go with different measurements. You can see when you have 10 measurements, they're overlapping. That's why it's hard to tell them apart. And then, but when you have, let's say 600, in that case, you can just separate it almost to 100% accuracy. So in addition to all of these, we want to see what can we do even better. So we went to 2 different approaches, much more complicated. So we did 1D convolution neural network, and we also did a multi-layer neural network. These kind of so we really want to see if these method works. These also works, but to train this kind of network or these two kind of networks, it requires much more computational time. You have to train for a lot of different scenarios, and then you can use it. But the benefit of line is the training can be easily done in a simple device like strawberry. The Pi stuff. Yeah, Raspberry Pi, which it's really cheap and easy. So these 2 kind of neural network, actually you will see. I forgot to put a comparison plot, but obviously you see 1D CNN outperforms all of the previous mentioned method. It's converging quickly to 100% when you increase the mean photon number or the number of data points you took. But it's at the cost of you spend more time on training, you getting more data from the beginning, and then you have to spend more computational time to train the network in the first place. And then the multi-layer neural network, and compared to this, obviously performs worse, but it's not better than the line. So, our conclusion is, we can kind of use either Bayes or either use outline, these kind of relatively simple method to significantly reduce the number of data points we took to separate two different sources. And then we can show that in some cases the neural networks outperform the Bayes, or in other cases in extremely low number of data points, the Bayes might give you a better success probabilities. And then in the end, okay, we successfully demonstrated that by doing this kind of simple statistical analysis, we can outperform state-of-art schemes for detection of photon statistics. Thanks.
Is it known what the optimal measurement is for distinguishing the thermal state from a coherent state in terms of error probability? Like Hellstrom measurement and quantum information?
Yeah. I think I'm not 100% sure of that.